All right, let's begin with chapter 23 of Earth History for Finlandia University. This chapter covers planets and their moons. We're going to take a quick tour of the solar system, starting from Mercury and heading on out to Neptune, and we'll even cover Pluto a little bit. How friendly of us. As usual, if you have any questions, feel free to comment them down below. Either I or another student will respond and have yourself a little bit of a conversation. We're going to start out on our tour of the solar system with a super brief overview of our solar system. It is thought to have formed some 4.6 billion years ago from a cloud of gas and dust. This is accretion theory. And the vast majority of the solar system is, of course, hydrogen. Hydrogen being the simplest of the elements, one proton, right? So what's going to be the most common thing we get? The next highest numbered percentage-wise element is helium. Why helium? Because it's the second simplest with only 2 protons. Everything else comprises 0.2% of the atoms in our solar system. So it takes a lot more energy to clump together to create your higher, more complicated elements, hence why they don't exist near the concentration. As said previously, the solar system formed out of this cloud of gas and dust due to contraction of gravity. Once you have a point, things swirl around it and collect in. This is thought to be the origin. As said here, at some point, the compression came to the point of fusion, thereby lighting the sun. That's the thesis. And it seems to work out pretty well. This thesis also takes into account things such as solar wind. Solar wind is similar to wind here on this planet, but it's not necessarily wind. Solar wind is a stream of positive ions and electrons that radiate from the sun at very high speeds. Essentially, solar winds blow throughout the solar system. And they blew most gases away from the inner part of the solar system. Hence, why the 4 inner planets are rocky and terrestrial in nature, and the 4 outer planets are gaseous, or the Jovian planets. This is the thought process as to why the planets exist in the places they exist. Big fat tables here of our planets in our solar system, starting with the 4 inner terrestrial planets, Mercury, Venus, Earth, and Mars. We tend to associate everything, of course, relative to Earth. So there's a lot of ones here, right? But you will notice these planets, to start out with, interesting in size. Mercury is very, very, very tiny. 0.38 the radius of Earth, 0.06 the mass of Earth. But the planet between the two is almost the size of Earth. 95% the radius, 82% the mass. That's interesting. It's not there is not a gradual linear relationship between distance, radius, mass, density, what have you, because Mars itself is about half the size of the planet. They all, by definition, have similar compositions, i.e. rocky with a metallic core. And once you start getting to Earth and on, you start stacking up your moons. Most people, I don't think, are aware of this, that Mars has, in fact, 2 separate moons. Interesting. Once you get beyond the terrestrial planets, you enter what we call the Jovian planets. These are your gas giants, starting with Jupiter, the largest planet in our solar system. About 11 times the radius of Earth and about 318 times the mass of Earth. But it's incredibly massive, not necessarily as dense. It's slightly denser than Earth. Interesting. And once you get here, of course, you run into liquid hydrogen surface with a liquid metallic mantle and solid core, i.e. a big amount of gas and a little teeny amount of planet creates the Jovian planets. The density of the atmosphere is not as established in the Jovian gas giants as it is on the terrestrial planets, so that's why we're not giving necessarily a percentage density compared to Earth. Instead, we're just saying There's a lot of stuff going on there. And the moon count is extraordinary. 62 some odd moons out here. And these numbers, in fact, do readily change as we go, which is itself very interesting. And then we can talk about our last two Jovian planets, Uranus and Neptune, are very, very far out there. Not that big, however, if we look at it. Comparing to the size of Earth, Uranus is only about 4 times larger than Earth is, and Neptune's right around that same size. Again, we have similar compositions to our previous ones, except we can't necessarily we can't call it for having a liquid metallic mantle simply because they're such less explored than Jupiter and Saturn. The distance of Uranus and Neptune is astounding, right? Almost 3,000 million kilometers away, 4,500 million kilometers away. Very far out there. You get to the point to where your images tend to be hazy unless you're using very high powerful equipment. And again, these planets also have tons of moons. Exciting, interesting, cool. So let's go through the planets one by one and talk about what's going on with them, so you can have a better understanding of the things that make up our solar system. We'll start with Mercury. Mercury is the closest planet to the sun. It is very small, as shown here, 2,400 kilometers in radius, but its closest to the sun gives it a ridiculous change in its temperatures. The sunny side of Mercury can hit as high as 427 degrees Celsius. Keep in mind, that's Celsius. That's not Fahrenheit. So that is over 4 times boiling water. On the non-sunny side, the shaded side of Mercury, you can get as low as negative 175 degrees Celsius. Water freezes at 0. So it is an incredible heat difference between the two. And it's also got a very slow rotation, thought to be about 3 days of rotation every 2 years. Over the course of 2 rotations of Mercury around the sun, 3 days lapse. There do appear, oddly enough, to be icy poles on Mercury. Its axis is perpendicular to its elliptical plane, meaning there's no axial tilt. And we talked in the last chapter about Earth's wobbling axial tilt, some 4.5 degrees, I think, something like that. Mercury doesn't necessarily have that. It has cold dark craters that shade from the low angle of the sun, allowing ice to form, even at these incredible temperatures. Venus is the closest in size and mass to the Earth, which we talked about in those paragraphs, and is hotter because it's right closer to the sun. There's no liquid water on Venus. There's no seas of CO2 to dissolve into and what have you. This issue with the lack of liquid water allowed water vapor and CO2 to combine to a runaway greenhouse gas effect. What we have on this planet with our greenhouse effect was much, much more elevated on Venus. Venus's atmosphere is about 90% denser than Earth. This is equivalent to saying there's 1,000 meters underwater to get yourself the density of Venus's atmosphere. Because of this, even though it's further from the sun, Venus, in fact, experiences hotter temperatures than Mercury, because Mercury essentially doesn't have an atmosphere, so it just kind of radiation from the sun hits it and then bounces off of it, whereas Venus, it hits it and it bounces back and forth the atmosphere, continuing this cycle, hotter and hotter and hotter. We're going to skip Earth because that's what the rest of the book has been, and we'll go off to Mars. Mars is about half the size, plus or minus, of Earth, and is in general very cold and very dry. This is due, of course, to being further away from the sun, getting less of its energy, and then also not having the atmosphere to trap heat. The polar regions, the top and bottom of Mars, contain ice that is in fact frozen carbon dioxide at around negative 120 degrees Celsius. It does have a comparable atmosphere to Earth at around 43 kilometers high, but there's not as much of it. Everything about this slideshow is constantly being updated in astronomy, in the day-to-days of science. It says here contains water, ice at the poles and the subsurface soils. I believe, as of the recording of this particular slideshow, that we have found concrete evidence of water in the subsurface soils on Mars. Super cool, right? And that's not necessarily surprising because there is evidence of prior liquid water on Mars, stream channels, rodent areas, lake beds, things along those lines. Mars was thought to be habited or possibly have civilizations way back in time because you can look at Mars through a telescope and you can see what look like riverbeds. So if there's riverbeds, there's probably rivers living there, right? When you think of aliens, the first thing you think of is a Martian. And there's a reason for that, historically speaking. Mars has a gigantic Grand Canyon on it. Valle Marinas. I'm sorry, I should know that better. About 10 times long and 6 times wider than the Grand Canyon with alluvial fans. We talked about alluvial fans in this class before. Alluvial fans are the way that water is deposited out of a river into a larger body of water, a delta, what have you. If we see alluvial fans on Mars, that's evidence that we probably had water to produce those, because on Earth you get these alluvial fans from the motion in these canyons due to water. Spirit and Opportunity were 2 rovers that went to explore Mars, to drive around. They, as I said before, found evidence of these guys out there. You can still, in fact, I believe Opportunity might still be rolling around every once in a while, actually. It's very interesting stuff. Here's an image of the canyon that we're talking about. And again, look at this canyon. Think about what we talked about with the way water moves on Earth. That looks a lot like what we'd expect water to do. That looks a lot like our Grand Canyon or what have you. Cool. Images of cross-bedded sands taken by Opportunity in 2006, providing evidence of, if you have sedimentary rock producing crossbeds. We talked about crossbeds way back at the beginning of this book, right? Those are evidence of beaches, of water-type environments. More compounding evidence and information that says Mars at one time had perhaps liquid water. The terrestrial planets, since we can obviously see their terrestrial part, the ground part, allow us to do geology on these foreign planets. Astrogeology is a very lively, very exciting field of research. In 1974, the Mariner 10 satellite went to Mercury and sent images of its surface back to Earth. This is the first time that we got a nice close look at Mercury. Kind of hard to look at Mercury, because you're essentially staring at the sun. We found that Mercury is heavily cratered, very moon-like, you could argue. Not necessarily evidence of erosion occurring from these meteorites as far back as, say, billions of years. No evidence of erosion, possibly no evidence of plate tectonics either. There is a magnetic field at Mercury, which is an interesting conversation, because if you don't have plate tectonics, which is part of the reason why we have a magnetic field, the heat leaving right from the core, we've talked about that. How do you get a magnetic field without evidence of plate tectonics? It's an interesting conversation to be had. If I told you there's a picture of the moon, you wouldn't bat an eye sideways at me, right? But that's actually a picture of Mercury. And keep that in mind, how ridiculous that is. In 1974, early 1970s, we flew a satellite to Mercury to take pictures of it. Absolutely fascinating. Venus, the atmosphere is actually rather opaque. As I said, it's super thick, right? 90 times thicker than Earth's atmosphere. So it's very hard to get a grasp of what Venus's ground looks like, because you got to dig through that pea soup atmosphere that it has. And actually, I believe, as of according to the slideshow, we are sending a probe to Venus to essentially crash through its atmosphere and take better readings, understandings of said atmosphere, as well as maybe, hopefully, possibly get a look at the ground of it. But from what we know there's very few craters on Venus. Most landforms are thought to be some 300, 500 million years old at that. What does this mean? Few craters, young life form? Well, you probably have active tectonics. You probably have the rock cycle working in some way, shape, or form to produce this younger crust on Venus. Very cool. Mercury, no evidence of tectonics. Venus, evidence of tectonics. Here is the volcano Mont Mons on Venus. It has produced large lava flows as shown in the foreground here. This, of course, would be not an actual picture of it. I believe this is just a artist rendering of the volcano. According to one hypothesis, a catastrophic series of volcanic eruptions altered the surface of Venus some 300, 500 million years ago. Possibly that's a reason for why Venus exists in the form that it exists, but more research needs to be done to understand what Venus is and how Venus exists in the form that it exists. Still, very cool things to think about. Why does Venus happen the way it happened? Scientists tend to use radar images from the Pioneer probe that went to Venus to produce a quote-unquote map of Venus. This is kind of what we think the topography of the planet looks like. Lowlands are in blue, highlands are in yellow and red, as is common with topography, and shown on the right there in that scale. And yeah, there's valleys, there's possibly what we would call lake beds, what we would call highland areas, right? Mountain ranges, everything. It's not that weird looking, to be honest, right? You could see yourself playing the game of Civilization on a map like this. In fact, I kind of want to download Civ 6 and see if there's a Venus map someplace, because that would be really cool. So, as said, Venus's surface temperature may be hot enough for the crust to remain plasticky, right? We don't quite know. Giving you some blob tectonics, which is not something that we have on Earth. It's possible. We know Earth is large enough to have retained much of its internal heat. How does that relate to Venus? Good question, because Venus and Earth are very similar in size, except that Venus is closer to the sun, getting more radiant energy from it, and it has a thicker atmosphere, keeping more of a greenhouse effect going on. So, lots of interesting questions with Venus. And lastly, we can move to Mars. Mars is a mix of old cratered terrain and younger tectonically altered regions. The largest volcano in the solar system is thought to exist on Mars, Olympus Mons. It is, get this, 25 kilometers tall, this volcano, and some 500 kilometers across. Just beyond stupidly large volcano. Sitting on the largest volcanic plain, the Thracis Bulge. And again, we have to bring up the conversation about blob tectonics here. We have parallel cracks along the Thracis Bulge, this large volcanic plain. Do we have evidence of possibly Earth-like tectonics? Is there active tectonics going on Mars? Strike slip faults, perhaps? Can we use what we've talked about from previous chapters to explain why Mars looks the way it looks? Interesting conversation, right? Here you can see some of the craters on Mars, some of its geologically older surfaces. We don't have these large craters very commonly on Earth because rock cycle tectonics chews them up, gets rid of them. So if you have lots of large craters like this sitting on Mars, sort of unaltered, that tells you the rock cycle hasn't gotten rid of them yet, which means that plate tectonics has not been doing its job. Here's a beautiful picture of Olympus Mons, just massive, massive structure, largest in the solar system, and right next door to us. It is very foreseeable that at some point in the not too distant future, mountain climbers may travel to Mars and climb Olympus Mons. That would be quite the feat. we can look at these older pictures of Mars, and we can see these huge parallel cracks near the Thracis bulge where Olympus Mons resides. They're neither folded nor offset. That's interesting, right? How do you get these cracks on some place like Mars? Scientists have speculated that the bulge and the cracks were formed by the rising mantle plume that is Olympus Mons. However, the absence of folding or offset movement provides evidence that the horizontal tectonics may not be active in the region. Lots of ongoing questions. How do the earthly understanding of geology play into non-Earth planets? Can we assume that the same mechanisms that happen on Earth happen in other parts of our solar system? Interesting questions. Here's a 3D recreation of Elysium Mons, one of the three large Martian volcanoes that currently Elysium rise. Again, this volcano is some 12.5 kilometers higher than its surrounding plain. Massive. Very cool stuff. As usual, I like to pause these questions so you can, if you want, pause the video and read them and try to answer them. I don't ask them in the class, but you can understand these questions. Good. That provides that you understood the chapter we've been talking about. All right, before we move on to the jovial planets, let's talk our moon. Our nearest neighbor, you see it every night, right? Well, assuming it's not a new moon. Our moon is one of the largest moons in the solar system relative to planet size. It is very heavily cratered, but also has smooth parts to it as well. It is thought that it was formed as a result of a large planet-sized bolide impacting the early soft molten Earth. The body broke up, and the two bodies broke and then reformed as, well, we now have the Earth and as well as part of the moon. The smooth plains up there on the moon are largely basaltic flows, which is interesting. And the areas are welded together by lava, which indicates heat and liquid, which may indicate tectonic activity. Cool stuff. The moon here, photographed from the Apollo spacecraft. I'm sure you're aware, we went to the moon in the 60s and 70s. And there's currently, as of recording this slideshow, a push for going back to the moon in the modern times. But taking a look at this image, you can very much see the craters shown around here and smooth areas as well, indicating flows of lava and also places that haven't been chopped up via plate tectonics. Most of the lunar surface is heavily cratered. You have craters within craters and stuff like that. The 6 Apollo manned moon landings between 69 and 72 answered many scientific questions as to the origin, structure, and history of the moon. Remember, we've sent lots of astronauts to the moon. That's fascinating. The amount of mathematical, mechanical know-how to get up there and walk around on another planet is absolutely amazing, at least to this humble presenter. According to the most widely held hypothesis, the moon was formed some 4.5 billion years ago. Remember, the Earth is around 4.6, so within the first 100 some odd million years of Earth's existence, you possibly have the moon. When it was struck by a Mars-sized object, when the Earth was struck by a Mars-sized object, blasting a cloud of vaporized rock into orbit. This is, again, when the Earth was more molten. It didn't crack like a bowling ball necessarily. The vaporized rock rapidly coalesced and therefore formed the moon. So essentially the moon was kind of formed in the same way the rest of the planets were formed. During its first 0.6 billion years or so, intense meteorite bombardment cratered the surface of the moon. And then the dark flat Maria, the flat parts of the moon, formed some 3.8 billion years ago as lava flows spread across portions of the surface. That's the idea from the evidence that we've been presented by looking at the moon. Is there modern volcanic activity on the moon? No, we don't think so. But there's evidence that there was once volcanic activity on the moon. Again, here's a brief highlight of the history of the moon, things we've already talked about. Is there liquid water on the moon? It's thought maybe in the poles. Most terrestrial planets seem to have liquid water at the poles, so the moon might have that as well. I can't remember as of recording this video if we've confirmed water on the moon, but I want to say we have. So correct me in the comments if you feel the need to. All right. Let's move on to the Jovian planets. Let's move on to the big gas giants way out there in our solar system. We'll get to meteorites comments at the end of this presentation. First one we'll talk about is the big boy himself, Jupiter, 71,000 kilometers in radius. Massive, absolutely massive planet. Mostly consisting of hydrogen and helium. This, of course, is because, right, those are the most common elements in our solar system. We are seas of liquid molecular hydrogen and helium, some 12,000 kilometers deep, floating around Jupiter. This is the liquid mantle I talked about at the beginning. At the bottom is some, look at this number. At the bottom of that liquid molecular molten outer core, if you will, mantle, is some 30,000 degrees Celsius pressure, heat, and 100 trillion times the Earth's normal pressure. That is massive, massive heat and pressure existing at the bottom of this mantle, this liquid mantle of hydrogen, of molecular hydrogen and helium. At this point, you have the H2 dissociating into two H's and the atoms compressing down. Electrons can become free-flowing at this point, and they flow essentially kind of like metals do on Earth, giving you liquid metallic hydrogen. And it is thought that this intense heat and pressure and this breaking, if you will, of the H2 bonds and freeing of the atoms of the hydrogen possibly generate the massive, massive magnetic field that Jupiter currently has. This is theoretical, of course. No one's actually been to Jupiter to see this happening, but picturing liquid metallic hydrogen flowing around at 30,000 degrees Celsius is fascinating. Here's an image of kind of what we imagine what's going on there. You have your rocky metallic core where your gravity is held, and then this right here, this liquid metallic hydrogen, is what we're talking about here, the 30,000 degree, 100 trillion times Earth's pressure disk. This rocky core exists simply because the massive amount of pressure doesn't let it become liquid. And then your outside massive liquid molecular hydrogen, atomic helium, floating around here, and then your gaseous part atmosphere on the outside here. Again, I will stress this is mostly all theoretical, but there's no reason to assume it's incorrect either. You can't really send a probe through 30,000 degrees Celsius liquid hydrogen and expect to get data results, right? And Earth drawn to scale over here to see the massive change in size. The inner part of Jupiter, that rocky core here, is still thought to be larger than Earth, maybe 10 to 20 times Earth's size. We have found within Jupiter's atmosphere H2, molecular hydrogen, helium, as well as NH4. I believe that's methane. We found water. We found CH4. No, sorry, NH4 is ammonia. CH4 is methane. There we go. And everyone's favorite part of Jupiter, the Great Red Spot. So big, Earth could fit in it. And it's essentially a giant hurricane, right? The spots and bands have existed for centuries on Jupiter. Galileo probe stopped transmitting some 130 kilometers when it went through this atmosphere. Here's a very nice picture of the gigantic always ongoing Earth hurricane that's happening in the ridiculous atmosphere that is Jupiter. The vivid colors are a result of computer enhancement to show off the turbulent flows and what have you of this exciting mixture of all these gases at these incredible temperatures, pressures, winds, what have you. Exciting stuff. This colorful, turbulent, complex cloud system of Jupiter was, of course, photographed by the Voyager space probes that went there. We talked about those a little bit ago previously. And you can see from this image, so this is a real image here, sphere on the left in front of the great red spot is the moon Io, and Europa landing over here. Io and Europa we'll get to after we get through the planets. We could talk about Saturn next. Lowest density of the planets, technically lower density than water. I don't know if you noticed that from the beginning block of chart. There we go, chart that we talked about. But beyond the low density, it's mostly similar to Jupiter. It is thought with your bands, your clouds, magnetic storms, your strong magnetic field, what have you. And the last thing we can talk about Uranus, Neptune, much smaller cousins of Jupiter and Saturn. An atmosphere similar, but without the complex molecules, simply giving you carbons, nitrogens, and oxygens, gaseous, what have you. Probably has molecular hydrogen, but missing the liquid metallic hydrogen mantle that exists in those thicker guys like Jupiter and Saturn due to not having enough size, not having enough gravity to push all that stuff together. Neptune, funny enough, has itself a great dark spot, whereas methane is thought to decompose into carbon and then under deep pressure creating diamonds. So imagine a hurricane of diamonds. That'd be kind of cool. And this crystallization causes heat and then derives winds and what have you. Uranus is very interesting because its magnetic field is actually tilted 58 degrees from its axis, meaning that where we have a north and a south pole on your compass, Uranus more has like an east and a west pole, which is very interesting. And Neptune, similar concept. Why is that the way it is? Common conversation had among astrogeologists. How could this stuff exist in the way it exists? The solar system is very unique and very mysterious and is very much worth your time and effort into learning if you find this stuff cool. Usual pausing here so you can try to answer these questions if you want before we move on. All right, let's talk about those moons. Let's talk about the moons of the Jovian planets. The first 4 moons of Jupiter are called the Galilean moons, usually, and because they were first discovered by Galileo in 1610. The fact that other planets have moons, specifically Jupiter, the wandering star that is so large you can see it sometimes during the day, that this has moons, really brought science and astronomy leaping forward from your days of Aristotle, and smart guy says it, just take it for its word. Very, very important in context. Nowadays, it's thought to have, Jupiter's thought to have some 60 moons, maybe more. Most of those are really, really, really small. The ones who care about the Galilean moons, Io, Europa, Ganymede, and Callisto. Of these 4, Io is the innermost of the moons, of these large moons that Galileo discovered. Probably it's thought about the same size as our own moon. And we have witnessed volcanic eruptions on this moon, sulfur volcanism, which is thought to be driven by heating from tidal sources. The gravity of Jupiter is literally pulling Io and shoving it around so much that it's causing volcanic tidalism, which is, again, all this stuff sounds so metal and amazing, right? Europa, another very interesting place. Maybe Europa contains life. That's a commonly thought hypothesis. It's a rocky body covered with water that being frozen. But that frozen water has been fractured into an ice terrain that may have a slurry lying beneath it. There are lots of very interesting videos about the possible life that exists in Europa, what it might be like. That when you finish this video, if you look it up, life in Europa, you're going to find a lot to dive yourself into. Ganymede and Callisto further out, both heavily cratered. Ganymede thought to have a magnetic field and tectonic evidence, and Callisto again may have water, liquid water on it. So if the next logical step after we get to Mars is, once we get past the asteroid belts, get to Jupiter, and well, when no chance you're going to land on Jupiter again, 30,000 degrees Celsius, 100 trillion times the pressure, you can perhaps go to these moons and see what evidence there is there before we head off to the diamond hurricanes of Neptune. Here we have right here, this blue guy here is a picture, an image captured by the Voyager 1 satellites that passed past Jupiter, showing a volcanic explosion here on Io. A volcano literally erupted at the time that we were able to take this picture. Super cool. This eruption is ejecting solid material to an altitude of 200 kilometers. That's a big old volcano. We can see here some of the smooth circular regions in the center, shown here, this photograph, possibly were formed when subsurface water rose on Europa, then froze, covering these old wrinkles, right? You have all this beaten up and expanding tectonic activity. Why is this smooth? Well, maybe it's smooth because liquid came up from the subsurface and smoothed it out. Evidence of below here is something that we might want to look into. Here's a cross-section of Ganymede, possibly explaining its magnetic field, possibly explaining how you can have water, ocean-like water existing on this very far away, very exciting, very active moon, right? This little line of water here between the ice and the high-pressure ice-water phases, as shown here. Right? The 4 main Galilean moons of Jupiter have so much like science fiction about them. Volcanoes erupting 200 kilometers up in the air. Possible world of ocean water existing below an icy surface. It's truly exciting sci-fi stuff. Except it's not science fiction, it's fact. We have the pictures here to show it. Right? We have the data here to show it. Another picture of Ganymede. Possibly these interesting marks, possibly the result of tectonic activity. And of course, we can move on to Saturn's moon. Saturn has some 31 moons that we've been counted. The most interesting of those would be the moon Titan. Titan is very popular in science fiction. Titan AE, I believe, is a movie from the late 90s, early 2000s. And the moon Titan itself is about as large, if not larger, than Mercury. Gigantic structure here. Atmosphere that's thought to have molecular nitrogen and methane in it, and appears to have evidence of possibly flowing liquids. Could there be water in the atmosphere? It's possible. Could there be simple organic compounds? Could there be life existing on Titan right now? These are questions that astronomers and astrogeologists would love to answer. Here's some radar images of Titan obtained in February 2015 that show a well-developed drainage pattern. Well-developed, not destroyed like on Mars, but instead well-developed, and apparent sand dunes shown up here. Previous images show features that may have been formed by tectonic processes. Titan may have young and dynamic surface volcanism, tectonic activity, erosion, impact craters, what have you. Essentially, Titan may be undergoing early Earth processes. And if early Earth processes gave us modern Earth life, maybe something like that's happening on Titan as well. Uranus and Neptune both have moons, but again, they're so far away at this point, you don't quite have the same amount of data that you do from, say, Jupiter and Saturn. Neptune, the moon, you may have heard of Triton. That's a very large moon of Neptune that has ice on it, we think, possibly water and or methane ice. And when you think of the Jovian gas-giant moons, you're probably picturing Saturn and its gorgeous rings. In fact, all the gas giants have rings. Saturn being the most famous, but Jupiter, Uranus, and Neptune. Well, you probably picture Uranus with the rings as well, but Jupiter and Neptune have rings too. But we can focus on Saturn. There are 7 major rings and thousands of smaller ringlets going around surrounding Saturn. Mostly about 10 to 25 meters thick, we think, but some of them are very, very wide, some 400,000 kilometers across. Mostly composed, we think, of dust, ice, and rock. Perhaps fragments of moons that haven't quite coalesced or once have been ripped apart. In fact, some of these rings have moons in them, or as it says their moons are held in herd portions of the rings. So you can imagine when we talk about the formation of Earth's moon, perhaps Earth at some point had this ring around it, similar to the Jovian gas giants, until the moon itself coalesced and formed. Image here showing Saturn's rings. If you say Saturn, you're picturing this, right? We all know what Saturn's rings look like. Here's a actual picture of Saturn's rings as taken by the Voyager 1, color, of course, enhanced. I think Voyager only took black and white pictures. But yeah, you can see all these thick rings here and the little teeny ringlets floating around. Really cool stuff, right? Lastly, let's talk Pluto. I know, it's so sad. Pluto's not a planet. Boo-hoo. We've all seen the cute cartoons and t-shirts. It was a planet until 2006, but modern definitions of planets and planetoids and dwarf planets, what have you, had to have Pluto and its co-orbit satellite Charon reclassified down. That being said, Pluto is still very interesting. It has atmosphere comprised of carbon monoxide, nitrogen, gaseous nitrogen, and CH4. And it is thought that maybe Pluto might have be a lost moon of Neptune or a Kuiper belt object, given its very interesting orbit pattern and its size and location. So these are all reasons why we don't really call Pluto a planet anymore, and instead call it a dwarf planet or a big moon, essentially. Yep, here's images of Pluto. Right, again, haven't really visited Pluto because it's really, really, really far away. But advantage, and also this ties into the last chapter. We talked about why we put the Hubble Space Telescope above the atmosphere. The ground-based telescopes can get you an image, interesting-looking image of Pluto, but Hubble, being outside the atmosphere, not having to deal with looking through Earth's atmosphere, can get you better realized images of Pluto and its moon Charon. Right. Lastly, let's come around and talk about the asteroids. There's a main belt of asteroids between Mars and Jupiter. Of these asteroids, some of them have been named, because they're very large, to Ceres. A 930-kilometer in diameter asteroid that exists in that Kuiper belt. Asteroids then change orbits frequently. Some orbit close to Earth. They collide with other planets. Not very uncommon. Since the asteroid belt is very, very active zone, there is a not zero chance that we may be struck by an asteroid in the next 1,000 years. A big one. Not necessarily like an Armageddon situation, the movie, not the biblical event, but it is possible too. And you're always going to hear astronomers and stuff talking about close calls with asteroids coming within X thousands kilometers away from Earth and stuff like that. It's cool stuff. It's essentially, it's like solar system's a big shooting gallery for asteroids. Those are asteroids. We can also talk, of course, about comets. Comet coming from the Greek meaning long-haired, funny enough. And comets, as opposed to asteroids, have very long elliptical orbits. Most of them spend their time out past Pluto and are thought to be mostly balls of water, ice, and methane. Comets don't necessarily have tails or just flying around balls of ice until they come close enough to the sun. When they come close enough to the sun, the dense ball, the nucleus of the sun, essentially starts to melt away, giving you a coma or some bright sun ions, and then a tail streaming off away, being caught by the solar wind, as shown here. That nucleus starts to melt, the water and the ice methane start to melt, and the speed of the comet combined with the solar winds radiating from the sun caused that beautiful comet-like tail that we have. Characteristic, as it says here. And then, of course, we could talk meteorites or meteoroids. These are fragments of asteroids or comets that travel into the inner solar system. They're all kind of describing the same thing. Asteroids are rocks, comets are ice, meteoroids are chunks of rocks and ice. We call it a meteor when it falls into the atmosphere. We call it a meteorite when it hits the ground. Most meteorites are stony meteorites. 90% of these are silicate, 10% of these are metal in composition, and they contain very interesting elemental properties, such as grains of olivine, pyroxene. These are words we talked about at the beginning of the chapter. Some contain organic compounds, some contain amino acids, interestingly enough, and some are almost entirely iron, such as nickel, mostly entirely metal, such as nickel iron compositions. They all vary vastly in what we have here. Here we have an interesting series of images, 8 images that depict the development of the ejecta plume formed when Deep Impact's probe collided with the comet Tempel 1 on July 3rd, 2005. Here we can see red arrows, boop, boop, highlighting shadows cast by the ejecta itself. The comet this comet in 2005 smacked into an asteroid. We literally shot a satellite at a flying by comet and then made little poofs, right? And this yellow arrow here on image A indicates the zone of avoidance in the upper range direction. These 8 images are taken within a second as the satellite popped into the comet. Of course, we also have a satellite that actually landed on a comet, took samples, and jumped back off of it again, but we aren't talking about that at this point, right? This is a conversation about what the asteroid is made out of. And that's pretty cool. In 2005, we shot an asteroid. We shot an asteroid with a satellite, and then like in 2015, we placed a satellite on an asteroid. Fascinating stuff. Here's a picture of a meteorite, i.e. a meteoroid, a part of an asteroid or comet that landed on the Earth. These are very cool. And there you go. That is a somewhat brief, hopefully interesting conversation about the planet and the inner solar system and the moons and what comprises the Milky Way. Not comprises the Milky Way, what comprises our solar system. The Milky Way has got a lot more than just this stuff. Hope you found it interesting. If you have any comments, of course, please leave them down below. I'll get to them in a reasonable fashion. And thanks for paying attention. Take care.